Hello friends, in this session we are going to discuss the concept of remainders, which is one of the most important part for CAT. So most of the questions of remainders are solved with the help of binomial theorem. So if there is any given number raised to power n which is to be divided by x and we are required remainder. In this case what we always follow is we divide n by x and we take out the closest multiple of x plus minus we take y. For example, if we have 13 raised to power 28 which is to be divided by let's say 2. So I can write this 13 as 12 plus 1 raised to power 28. Or if we have 13 raised to power 28 which is to be divided by 5, we can write this 13 as 10 plus 3 raised to power 28 divided by 5. So in these kind of cases, if we expand x plus y raised to power n binomially, it is equivalent to nc0 x raised to power n plus nc n minus 1 x raised to power n minus 1 into y plus nc n minus 2 x raised to power n minus 2 into y square plus so on up till nc n minus 1 into x into y raised to power n minus 1 plus ncn into y raised to power n. The power of x is defined by the difference of these two values, and the power of y is equivalent to the number in the base. So in this case we will not get into a detailed study of binomial theorem. We just need to understand one part, that what is going to be the expansion of x plus y raised to power n. So if we divide this number by x, in that case we can observe starting from first term till second last term, each and every term contains x or the higher powers of x, which means this entire value in the bracket is a multiple of x. So remainder comes out to be last term only, which is going to be ncn y raised to power n. So the value of ncn is 1, so it results in only and only y raised to power n. Now in this case the value of y can be positive or negative. Like I could have written this 13 as 14 minus 1 raised to power 28 divided by 2, or this 13 as 15 minus 2 divided by 28 divided by 5. So in these kind of cases the value of y is always less than the divisor. Whether it is positive or negative, it is going to be less than the value of x. So my remainder comes out to be plus minus y raised to power n straight away. On the other side, if I divide the very same value by x square, in that case we can observe that from this term towards the left, each and every term contains x square or the higher powers of x square. So remainder comes out to be last two terms of this expansion. So nc n minus 1 equals n into x into plus minus y raised to power n minus 1 plus minus y raised to power n. So these theorems are the most important theorems. All the questions coming in exams are doable through this particular theorem only. Still, there are theorems which we can always discuss so as to understand the concept of remainders further. There is one theorem called Fermat little theorem. In this case, we can say a raised to power p minus 1 when divided by p leaves a remainder of 1 if HCF of A and P is 1, which means A and B are co-prime to each other. Only then we can use Fermat little theorem, wherein A raised to power P minus 1 divided by P leaves a remainder of 1. For example, if I talk about, let's say there is 2 raised to power 38 divided by 3 and we are required remainder. As we know, 2 and 3 are co-prime to each other. So we can say 2 raised to power 2 divided by 3 always leaves a remainder of 1. So if your power is any multiple of 2, a remainder is always going to be 1. So this is the extended form of Fermat little theorem, wherein we have to choose power in the multiples of p minus 1 also, so as to make our job easier. On the other side, Euler's theorem states that if there is a number n which when factorized will be of the form p raised to power a into q raised to power b into r raised to power c, so on, where p, q, r are my prime numbers. In that case, we have to calculate the value of phi n. So phi n basically means the number of numbers which are less than n and are co-prime to n. It is equivalent to 1 minus 1 by p into 1 minus 1 by q into 1 minus 1 by r, likewise product in the very same form finally multiplied with n. So Euler theorem states a raised to power phi n when divided by n, remainder is always 1 if HCF of a and n is 1. Again, these two numbers should be co-prime to each other. Now Fermat theorem can be applied to prime numbers only, whereas Euler theorem can be applied to composite numbers as well, right? So like in this case, if I take an example, let's say we have to divide a number by 100 and we are required remainder. So this 100 is 2 square into 5 square. So Euler number for 100 is going to be 1 minus 1 by 2, which is 1 by 2. 1 minus 1 by 5 is 4 by 5 multiplied by given number 100. So 110 gets cancelled out, results in 40. Which means any number raised to power 40 divided by 100, remainder will be 1 if a and 100 are co-prime to each other. Like in this case, if I take 3 raised to power 40 divided by 100, remainder is 1. Right, 7 raised to power 40 divided by 100, remainder is 1. Or you take 13, 17, right, you take 23, 27, you can take any numbers for that matter. Right, so whatever number is co-prime with 100 leaves me a remainder of 1 when power is a multiple of 40. Let's say we have to divide a number by 16. In that case, your Euler number comes out to be, because we know 16 is in the powers of 2 only, so 1 minus 1 by 2 is 1 by 2 multiplied by 16, which comes out to be 8. So any number which is co-prime with 16 raised to power 8 always leaves a remainder of 1. So this is again quite helpful, but till date we haven't seen any requirement of such a theorems in exams. So if you can avoid them, there is no harm. So this concept in itself is important, right, which is the value of phi n. It helps me to find number of numbers which are less than n and are co-prime to n. This is very important. Please always keep this thing in your mind. Now further is Builtin remainder theorem, which is very important. So questions do come in exams based on the same. So in this case, we can say p minus 1 factorial when divided by p leaves a remainder of p minus 1, or we can say minus 1 also, right? As we have discussed earlier, if remainder is negative, we need to add divisor to it so that my remainder becomes positive. So either we can say p minus 1 or minus 1, it is the same. Another theorem associated to the same which helps me to apply this particular concept is when there is a sum like this. So 1 multiplied by 1 factorial, 2 into 2 factorial, 3 into 3 factorial, so on up till n into n factorial. This is always equivalent to n plus 1 factorial minus 1. So it can be observed from here also. If I take only first term, it can be written as 2 factorial minus 1. If I take first two terms, they add up to 5. It is equivalent to 3 factorial minus 1. If I take first three terms, so this is 6 multiplied by 3, 18, 18 plus 5 is 23, which is equivalent to 24 minus 1, which is 4 factorial minus 1. So out of this, we can deduce this, that it is equivalent to n plus 1 factorial minus 1. Now, let's have a look on questions, how we have to solve them. So we are required remainder when this number is divided by 2. As we have discussed in case of binomial theorem, that my remainder is going to be plus minus y raised to power n. So my focus is always on that I have to choose value of y as 1. If it is 1, it's fine. If it is not, we have to do some calculations such that it becomes 1 or minus 1. So like in this case, we can see 121 divided by 2, remainder is 1. Whatever the power is, doesn't make any difference. 1 raised to power 360 comes out to be 1. If this number is divided by 3, which is 121 only, right, when 121 is divided by 3, remainder is 1. Whatever the power is doesn't make any difference, answer is 1. Likewise for 4. 121 divided by 4, remainder is 1. Whatever the power is, it is 1. In case of 5, we just need to focus on units place of the number, which is 1. So remainder is 1. In case of 6, again here remainder is 1. Now in case of 7. So 7 multiplied by 1 is 7, leftover is 51, 7 sevens are 49, leftover is 2. In this case, a remainder comes out to be 2 raised to power 360. It is not 1 straight away. Now we need to modify it to make it 1 or minus 1. Now here we have to find powers of 2, which when divided by 7 leaves a remainder of 1 or minus 1. And as we have discussed in case of little Fermat theorem, because 7 is a prime number, so any number raised to power 6 divided by 7, remainder is 1 if these two are co-prime to each other. Or if the power is multiple of 6, remainder is always 1. As we know 2 is co-prime with 7. So 2 raised to power any multiple of 6, remainder is 1. Because 360 is a multiple of 6, so remainder comes out to be 1. Now in case of 8, so one way of doing this will be 8 multiplied by 1 is 8, leftover is 41. 8 5s are 40, leftover is 1. So 1 raised to power anything, remainder comes out to be 1. We can also use Euler theorem in this case. So Euler number of 8 comes out to be 1 by 2 into 8, which is 4. So as we know, 121 is odd, which is co-prime with 8. So 121 raised to power any multiple of 4, remainder is 1. And we can clearly see 360 is the multiple of 4, so remainder is 1. Now in case of 9, 121 divided by 9, remainder is 4. I am just adding the digits, 1 plus 2 plus 1 is 4. So one way of doing this will be that we simplify 4 raised to power 360. So we have to find a power of 4 which when divided by 9, remainder is 1 or minus 1. So we can clearly see 4 cube is 64, which when divided by 9, remainder is 1. So if I represent this number as 4 raised to power 3 whole raised to power 120. So it becomes 64, which gives me a remainder of 1. Whatever your power is, remainder is going to be 1 only. Or in this case again we can compute Euler number. So Euler number of 9 comes out to be 1 by 3 into 9, which is 3. So if your power is any multiple of 3 when the number is co-prime to 9, so remainder is 1. And we can see power is a multiple of 3. In case of 10, units place in itself comes out to be my answer, which in this case will be 1 itself. In case of 11, this 121 is a multiple of 11, so remainder is 0. In case of 12, again we can see, so 12 into 10 is 120, remainder is 1, whatever the power is, it is 1. In case of 13, now this 121 is 9 less than 130. So we can say remainder is minus 9, or we can say remainder is plus 4, because 13 minus 9 is 4. Or you can also go with 13 into 9, which is 117. So remainder is plus 4. So here value comes out to be 4 raised to power 360. Now one way of looking at this is, because 4 is co-prime to 13, we can use Fermat little theorem here, according to which any number whose power is a multiple of 12 divided by 13 leaves a remainder of 1. So we can see this 360 is a multiple of 12. So remainder comes out to be 1 straight away. In case of 14, again we have to use the very same concept. So 14 multiplied by 8, if I go with, it comes out to be 112. And if I go with 14 into 9, so this value comes out to be 126. Now we can use any of the two to solve my question. We just need to pick that value which is closer to 121. So 126 is closer to 121 as compared to 112. So better is to go with 126. So I can say 121 divided by 14, remainder is minus 5, because 126 is the closest multiple. Power being even, negative sign will be eliminated. So results in 5 raised to power 360 divided by 14. Now again, as we know that this number is co-prime with 14. So we can try calculating iler number for 14, which is 1 by 2 into 6 by 7 into 14. 14 gets cancelled out, results in 6. Again we can say if power is a multiple of 6, in that case remainder is 1, and here my power is a multiple of 6, so remainder comes out to be 1. Likewise in case of 15, so 15 into 8 is 120, and it is 1 more, remainder comes out to be 1. So here anyhow the examples that I have chosen leads to a remainder of more or less 1 in all cases. So let's change the value and let's do it again. Let's say instead of 121, if this number is 123 raised to power 360, let's see what all changes will come in picture. Because this number is odd, with 2 still remainder is 1. In case of 3, we need to add all the digits, which adds up to 6. 6 is a multiple of 3, remainder is 0. In case of 4, we know 124 is a closer multiple of 4. So it gives me a remainder of minus 1 raised to power even value. A remainder comes out to be 1. In case of 5, we are required units place of this number. Cyclicity of 3 is 4. When we divide power by 4, it gives me a remainder of 0. So 3 raised to power 4 is 81, which gives me 1 as the units place of this number. So 1 is the remainder when it is divided by 5. So in case of 10 also we can write it straight away, the remainder is 1. In case of 6 now, 123 raised to power 360 gives me a remainder of 3 raised to power 360 when divided by 6. Now in this case it is very clear that there is 3 which is common between the two. So if there is a number which we can cancel out, you can always carry the process of cancelling the numbers. So it results in 3 raised to power 359 divided by 2. Now if I solve it further, so 3 divided by 2 leaves a remainder of 1. We just need to keep one thing in our mind: with whatever value we have cancelled initially, we have to multiply at the last with the very same number in order to get original remainder back. So here remainder comes out to be 3. The reason behind the same is, first of all, the question was 3 raised to power 160 divided by 6, what is the remainder? When we cancelled out values, question boils down to 3 raised to power 359 divided by 2, what is the remainder, which comes out to be 1. So if I see that dividend equals divisor into quotient plus remainder, and if I take these set of values here, 3 raised to power 359 equals 2 times quotient plus 1 as my remainder. As I am required my divisor to be 6 and this number to be 3 raised to power 360, it is very clear we have to multiply the equation by 3. The moment you multiply it by 3, it becomes 360, it becomes 6q, and it becomes 3 now. Right? So I am giving you a proof such that you shouldn't think of that we have to go for like cramming. There is no cramming required. So we can just do it like this. Right? So in case of 7 again, if there is a number which is co-prime with 7, right, raised to power a multiple of 6, remainder is 1. And here it is 7 into 1, which is 7, left over is 53. 7 7 is 49, remainder is 4. Because this number is co-prime with 7, power is a multiple of 6, remainder is 1. Likewise in case of 8 now, we have already calculated the iler number for 8, which is 4. So 123 being odd, power is a multiple of 4, remainder is 1. In case of 9, if I add digits of this number, so 1 plus 2 plus 3 adds up to 6. If the power of this number is any value which is greater than or equal to 2, so because this number contains 3, and if the power of 3 is 2 or more than 2, it is always a multiple of 9. So we can say remainder in this case comes out to be 0. In case of 11, we can see 123 is co-prime with 11. So any number raised to power a multiple of 10 divided by 11 leaves a remainder of 1. Here 360 is a multiple of 10. So remainder in case of 11 comes out to be 1. Likewise in case of 12 we can say, right, so this number is co-prime with 12, 123. Sorry, it's not co-prime. 3 is the common factor. So 123 raised to power 360 divided by 12 results in a remainder of 3 raised to power 360. So 3 is the common factor which we can cancel out, results in 3 raised to power 359 divided by 4. So 3 divided by 4, remainder is minus 1, power being odd, it comes out to be minus 1 only. We have already cancelled out with like 3 which is to be multiplied now. So it becomes minus 3. As my divisor is 12, if I add 12 to this, final remainder comes out to be 12 minus 3 which is 9. So now 13 and 123. So 13 is co-prime to 123. So if power is a multiple of 12, remainder is 1. Likewise, we can solve many more questions based on the same concept. Right? You can always change the number to do a lot of practice on each and every type of divisor, because you will find that it is very easy to find remainders. Right? You can think of any number, even larger numbers, whatever size it may be. So the theorems which we have just discussed will help us a lot in determining the remainders with ease. In next session, I am going to discuss more questions based on remainders so as to give you a holistic approach on remainders. Thanks a lot. Stay connected for my next video.